Okay, so I think we can get started. So it's a pleasure to have Andreas, and he's going to talk to us about wormholes, eigenbranes, and ensembles. So thank you, Andreas.
Okay, hi. Yeah, thanks again for the invitation. It's a pleasure to speak here. Okay, so what I'll be talking about today. So the main goal, I guess, is to discuss the role of wormholes and branes or eigenbranes in reconciling geometry with quantum mechanics. And we'll do so working within a two-dimensional dilaton gravity. Well, basically JT gravity, but it also applies to other models. So first we'll see how wormholes can enable geometry to accurately capture average properties of late-time correlators of chaotic quantum systems. Now, whilst this is nice, this also raises a puzzle, as I will explain, and most of you already know, because this theory of gravity with wormholes will turn out to kind of generically describe an ensemble average of theories. And so by consequence, one might fear that gravity is sort of too stupid a theory to capture any microstructure, and is always, in some sense, describing an ensemble. I want to point out that in this set of theories, that's not the case, and that there does exist a geometrical description, well, quote unquote geometrical perhaps, of individual draws of the ensemble, and so of microstructure of, let's say, one individual quantum mechanical system. And the idea or the conclusion will be to consider this gravity theory in a background of branes, and the branes will be like branes in string theory, but then for spacetimes to end up unknown. And these branes, which we'll call eigenbranes because they encode the eigenvalues of a Hamiltonian, they deform the gravitational theory, just like if you would compute a closed string observables for a string theory on a set of branes, then those branes also deform the theory. That's what happens here too. Oh yeah, thanks to Thomas and Henri for collaboration on this topic last year. Okay, some general intro, totally redundant still. So there's about 1 million versions of what one might call an information paradox. And each of them is like a thought experiment where an observer outside of a black hole does something, and we do the calculation that corresponds to that in two different ways. Either we use general relativity or, well, quantum field theory on a fixed background, or we use holography, which then basically means we use quantum mechanics or quantum field theory, whatever. And often these two give quite different outcomes, especially when we go to late time extreme regimes. And so what this means is, well, it's not really a problem or anything. It's just that holography is describing quantum gravity and the other picture is classical gravity. So it's more revealing that quantum gravity behaves differently than classical gravity. And we sort of need to figure out, how precisely it behaves differently. So each version of what we could call such a paradox is really a call for an additional understanding of how quantum gravity works. And so in a sense, all these problems there, well, not in a sense, just it's the case that all these problems are teaching us what the rules of quantum gravity are and how it can emulate a quantum mechanics system. So we identify small problems and then we learn something about gravity. And so one important aspect, or at least or interesting aspect for me, is how geometry can encode microstructure, or, well, states of a quantum system or whatever. Okay, so here we'll focus on one such call for a geometric understanding of microstructure. And we'll consider, basically JT quantum gravity or another dilaton gravity. that's dual to some chaotic quantum mechanics with a discrete spectrum. So consider a thermal two-point function in such a system, because I assumed it was discrete. It becomes a sum like this. And so we construct a boundary system such that it has a pure JT gravity dual at low energies. Now my question for the rest of the talk is basically if that question or that sentence even makes sense. Like, can pure gravity really describe the low energy features of a certain quantum system? If that's the case, then we should be able to reproduce this sum exactly from some quote unquote geometrical calculation. Now, that may look easy, but when we make some pictures, it starts looking more and more hard, I feel like. So I think, yeah, probably you'll see pictures like this. So if we plot a two-point function like this, schematically, it will look something like this red curve. So the curve will decay smoothly at early times, basically because this is roughly like a Fourier transform, and an early time Fourier transform can see any microstructures, so it would treat the sum as an integral and you get something smooth. But at exponentially late times, the Fourier transform can distinguish the delta function, so to say. And so what we get is instead this sum of erratic oscillations, because all these things, we can ignore beta, for example, and then these are just phases that we're adding up. And so we get something that's wildly fluctuating. So we get some erratic oscillations around some, well, in general, non-zero average profile, which for a two-point function is a ramp and a plateau. And this average profile is actually super easy to see in this sum. You see that there's like, it's like a sum over two energies, but the terms where EA equals EB, they don't depend on time, so they just give a constant. And that constant's just always there, and whatever we do is fluctuating around that. But clearly, if we're too stupid and approximate the sum by an integral, then we won't get something like that. Okay, so yeah, one comment is that the details of these erratic oscillations, they depend very sensitively on the microstructure. And microstructure here, I mean just the eigenvalues and the matrix elements of the quantum mechanics system. If I change the eigenvalues by a bit, then the fluctuations will be different. It's quite obvious, I think. Okay, so what does classical gravity predict? Well, it essentially is a curve that is similar at early times, but it continues to decay all the way to zero, which is roughly what cluster decomposition is telling us. And so if we compare classical gravity to, well, let's call this holography, or to be proven to be quantum gravity, then we see that the early time behavior is captured quite well by classical gravity, and it should. But at late times, things go wrong quite badly. And that's, of course, because classical gravity doesn't know about microstructure. And in fact, it doesn't even know about discreteness. And we can see that very clearly by comparing these plots. If it would know about discreteness of the system, then we might think it has something like a plateau. And if it knew about microstructure, then it should have these oscillations too. Okay, so I think this difference between what holography predicts, well, not many people think, what this difference predicts says is that we need to sort of figure out what's going on with gravity such that it can reproduce that red curve and not only this blue curve. Now, because this curve is so noisy, it seems sort of difficult to get it from gravity calculation, or well, any field theory calculation, let's say. Any normal calculation won't give that. And so as physicists, I guess we sort of know better than facing complex problems with a lot of noise head on. And we should first do something simpler and basically block out the noise and make an easier problem for ourselves. So that's what we want to do first from the boundary point of view. So we want to sort of write a correlator that is quite similar to the red curve, except that it strips off the erratic oscillations. And the way I want to do that is by taking an average of theories. So I compute a two-point function in a system with a given Hamiltonian, and then I repeat that for many, many Hamiltonians and average that with some weight. Now, if I do this in a particular way, meaning I take the measure to be roughly that of a random matrix theory, then that gives me what I want. That gives me a curve that only strips off the erratic oscillations. And that is because, well, that's roughly what random matrix universality is saying is that that's precisely the fact that random matrices are well suited for describing average properties of chaotic quantum systems at all times. And so I could do other types of averaging here that give me the same answer, but they would still have an effective description of as random matrix theory. And so, yeah, I'll be studying, or in the boundary theory, we'll be studying something like random matrix theory. Now, these random matrices give some quite precise predictions. So if I compute a two-point function in random matrix theory, for example, then I get something that looks like this. I just, again, wrote things out in an energy basis or something, and then there's some smooth kernels here. This rho is like the level density, which is like the probability to find a level at energy EA and EB in this random matrix ensemble. And then I have some smooth function representing whatever becomes of my my operator matrix elements. So this rho function, it's like it's basically the product of two coarse-grained spectra, let's say, of our system, except that when the energies are very close together, something happens, and what happens is that the probability drops to 0. So if the energies are far apart, random matrix theory doesn't do anything. But if they're close together, it's saying that's very unlikely, because in chaotic systems, the energy levels are seldomly close together. Okay. Anyway, that's not too important for the talk. The point is that if we plot these random matrix theory functions, correlation functions, then they give us indeed the sort of correlators that we expect, like these smooth profiles that accurately represent our late-time correlators, but without all the noise. Yeah, we can do this for higher points functions, whatever. Okay, so now we have a simpler version of our quote-unquote paradox, or just problem, is that if you have an average of binary systems, then we have a curve that has a behavior like this that doesn't go to 0 at late time and has some interesting random matrix structure. But classical gravity says nothing at late times. Everything goes away. And so our question becomes basically, what is the geometrical interpretation of these average curves? And more importantly, how does geometry capture random matrix universality of chaotic quantum systems? The basic principle here, I think, is by now quite well known in our community, is that we should account for wormholes in the gravitational path integral. So, yeah, this means, for example, when you compute a partition function in two-dimensional gravity, well, gravity in any number of dimensions, you just allow wild things to happen in the bulk, and those wild things are like a nucleation and annihilation of baby universes, for example.
Can I ask a question?
Sure.
Just to check whether we're on the same page. I mean, when you say classical gravity, I think what you mean is what we mostly call semi-classical gravity, some expansion,
Yeah.
a bit of expansion in GH bar.
Yeah.
And from the viewpoint of that, it would have been perfectly consistent, or at least not wildly surprising, if there was no explanation of this non-zero plateau, because that plateau happens at some sort of infinite time in that expansion. So would you agree with that? I mean, just in the sense of
there's no problem.
I think
there's
that it's
nothing
sort of
wrong with
amazing
classical
that
gravity,
it's
but
possible to find it at all.
But the quantum theory should explain everything, right?
Yes, but the fact that you can also derive it in the gravitational path integral if you're sufficiently clever.
That's true.
That didn't have to happen. I mean,
No,
it's
it
amazing
might
that
have
it
been
happened.
something more, yeah, that were something much smarter than the gravity path integral. Yeah,
Yeah.
true.
Yeah.
No, I agree. Yeah, that's cool. That's very cool. Okay, so yeah, what we do is we sum over these geometries that are like wormhole geometries. So you don't only allow like small fluctuations of the metric, you also allow fluctuations where the topology changes at a certain instance in time, and then the universe splits off, and at a later point in time it reattaches and stuff like that. So in 2D gravity, this means basically a sum over Riemann surfaces of arbitrary genus. Okay, but now for this part of the discussion, I want to focus on boundary correlators. And yeah, that becomes sort of a little bit more intricate, not that much. So via the holographic dictionary, we know that if you compute a boundary correlator, any insertion of a boundary probe, sort of similar to shooting a particle, a matter particle into the bulk, and then we're just computing propagators of these matter particles through the bulk. But now when we also include these wormhole geometries, then of course we need to account for the possibility of the matter particles traveling over the wormhole geometries. In particular, in this 2D model, the interesting thing that happens is that the particle can sort of wind around the wormhole. So it can get in this wormhole and sort of traverse it a certain number of times. And so these sums become quite a bit more complicated. Because now we don't only have an infinite sum over genus, we also have an infinite sum over particle winding number around any of the handles on any given genus. So that looks kind of annoying. But still, it turns out that we can compute these infinite sums quite exactly. And yeah, I won't detail the calculation too much, but just say a few words about it. That it nicely combines the fact that, first of all, we can compute the GAT path integral on any fixed geometry. And then also some real cool math, I think, by Mirzakhani and company about the volumes of moduli spaces of Riemann surfaces and the mapping class group. So the thing I want to say about this mapping class group, which I think is sort of intuitive for you all to understand, is that so we have basically when we compute these amplitudes, say on any given surface, on any fixed genus G Riemann surface, we have these infinite sums over particle windings, but this infinite sum will cancel with another infinity that exists. And this infinity that we divide out by is we can think of as no, not we can think of are large diff redundancies in gravity. And what they basically say is that there's many equivalent ways to describe a certain Riemann surface. Like, for example, we know that a torus is a invariant under modular transformations, and that's basically it. So one nice way to visualize the mapping class group is to take, for example, the torus and just highlight a geodesic on it. So we can, for example, have a torus, and then we highlight a geodesic on it around one of the cycles. And then we see if we apply an S transform to that, then the geometry we get afterwards isn't quite doesn't look the same anymore. Like the geodesic has turned into a different geodesic. And so I think you see that this sum over particle winding is actually equivalent to the sum over elements of the mapping class group. And gravity tells us that that sum is something we need to divide by. And that means that all these infinite sums, they basically collapse to just, basically one amplitude that we need to calculate. And that's why things simplify quite a bit. Okay. So we can do these sums in the end, because there's no infinities anymore, and we can compute every given amplitude. And well, the result, I think, it's not quite surprising on hindsight, is that we reproduce correlators from random matrix theory on the nose. And yeah, as I told you in the beginning, without wormholes, that would completely fail. You would get a totally different correlator at late times. And so the conclusion of this is that gravity plus wormholes explains the average behavior, the average late time behavior of correlators of chaotic quantum systems. I think this also raises, well, many people think this also raises a puzzle, because there's no obvious averaging going on the left-hand side here of this expression. I'm just computing a gravitational path integral. And yet we obtain an average correlator. And so you may think that that's unavoidable, that that's the best that the gravitational path integral can do. And that it always sort of computes an average, sort of oblivious to the details of a theory, and can never produce a noise. But in the remainder of the talk, I want to present an example of how, in fact, geometry can also describe individual draws of an ensemble and microstructure. Yeah, something else which I wanted to point out here is that the calculations of this type, they're, I mean, let's say 10 years ago or something, I think no one would have been surprised if you said that a certain minimal model in two-dimensional string theory is a random matrix theory. We all knew that. And yeah, okay, there's a new element is then to identify JT as one of those minimal models as a string theory. But I think maybe the real leap here is that in this calculations like this, you really identify the random matrix, which was maybe more of a formal object back in the day, as really the Hamiltonian of dual quantum systems. And so all these things which we called minimal string theory, we can also view as two-dimensional gravities, and in those cases the matrices are really just Hamiltonians. So I think that's a nice change of perspective. Okay, so what I want to explain to you is that the individual draws of the ensemble are represented by considering gravity on some background of specific branes. But before going into the details of how that goes in these delta and gravity models, I want to sort of give you a feeling for why branes should help in gravity in general. Therefore, I want to consider a toy model for correlators, which we know as the spectral form factor, where I just put all the matrix elements of the operators to 1. And then this becomes like the 2-point function becomes a product of partition functions. And if we plot that, yeah, we get a curve that looks very similar to these 2-point functions at late times. So yeah, I think this is a familiar story. If we compute a partition function in gravity, we do the sum over geometries I just explained. But now if we compute the spectral form factor, then we have a gravitational path integral with more than one boundary. We have 2 boundaries. And then of course we'll be summing over all geometries that end on those 2 boundaries, including potential wormholes connecting the 2 boundaries. Now wormholes like this, they don't exist in, let's say, the square of the top of this calculation on the top. And that means that there is a factorization puzzle in gravity quite in general, unless if something quite miraculous happens to these wormholes. And the factorization puzzle is that the square of the partition function is not the partition function squared. Well, a priori you would say, well, of course, it's perfectly fine. Those pictures make perfect sense. But that's, yeah, it sounds weird if we want to think about it in the sense of, let's say, the SCFT, because then the partition function is just a number. It's literally sum over energy eigenvalues e to the minus beta energy. So how can that thing have a non-trivial correlation. And so, yeah, there's two ways out of this. One option is that wormholes, they're not real, don't count them. You never have this problem. But yeah, we sort of introduce wormholes to deal with another problem, and we can't get by without them. Because without wormholes, all correlators decay to zero, as we saw. And wormholes give a nice intuitive picture of why correlators in gravity should never decay to zero. Basically because they can create shortcuts between any 2 points in space-time, and then everything affects everything or something. And so, yeah, they're a clear improvement over semi-classical gravity, and so we need them. Now, the second option is that perhaps integrals of gravity with wormholes naturally always compute ensemble averages. Because, yeah, in an ensemble of theories, it's obvious to get correlations. But then this brings by the puzzle I mentioned earlier that suggests that gravity, the way we look at it now, is maybe not rich enough to capture microstructure. And there's always an ensemble washing away the details. I think there's a third option to this, which is at least the one that's I think quote unquote true in these lower dimensional models, is that there are wormholes, but there's also other stuff. And the other stuff will help with factorization.
Before you go on, could you just explain again what downside is of saying of the ensemble interpretation? That went a little fast for me to understand it.
Well, I think that the downside is that we want, I believe that ADS-CFT or something suggests that we want to describe one single quantum mechanical system. And if gravity can't do that, that's a severe constraint on what we can do. And I think it's an important, maybe I'm not saying that's necessarily a priori wrong. I mean, it could be that every gravity theory is describing an ensemble, and that we should forget about ADS-CFT and only think about averaged ADS-CFT or something. But I just don't think that's correct. And I think that there are gravity theories that do correspond to individual quantum systems. And then I think I want to study those preferably. Is that okay?
Well, let's see if I can follow that. So, I mean, let's just take for granted that the correct theory had better be a unique quantum mechanical theory and not an ensemble.
Yeah.
And but it could be that semi-classical gravity is capable of computing certain quantities in that correct theory. And depending on how cleverly you apply it, I mean, we already knew it was capable of computing the thermodynamic entropy, as Gibbons and Hawking discovered. Now we understand it can even compute the page curve. If you sort of do the right tricks. But that doesn't mean it's the right theory. It's just that you can extract more and more from it if you know what to do. But you could also ask, is there some dual to just semi-classical gravity, whether or not that's the correct theory of nature, right? You could ask whether there's a boundary dual, and I don't see anything wrong with I mean, maybe it's right, maybe it's wrong, but I don't see anything obviously wrong with saying that is an ensemble.
Yeah, no, there's not. I don't think there's anything wrong with that. But I guess I would prefer it and I think it's true that the gravitational path integral does know a little bit more than just that, or it can know a little bit more.
But in a higher dimension, it could be even an ensemble of states. That's enough to reproduce these properties. And it's quite natural that Euclidean gravity, going to Euclidean, you're doing thermal ensemble hiddenly, implicitly. So that could correspond to ensemble of states.
But the thermal ensemble is an ensemble of states.
Yeah. And that's enough.
And there's a problem for the thermal ensemble. because the square of partition functions in the terminal ensemble is still the square of partition functions in the terminal ensemble, right? Z of beta 1 and Z of beta 2 are terminal ensembles, basically. But there's no, yeah.
Yeah.
If I take the product of two terminal ensembles, it's still the product of two terminal ensembles and not, there's no other ensemble appearing.
Yep. Yeah. Okay. Anyway, yeah. Let's. Yeah, I would think.
No, but I agree with what was brought up, that there's nothing obviously wrong, because you could say, well, the gravitational pattern is too stupid. But then I guess I want to know what's the smart version. What is what is smart enough? And I feel that here there's an example where already the gravitational path integral itself knows quite a bit. Not everything, but knows some things. Either way, if the question I really want to answer is, you give me a Hamiltonian of a system, what is the bulk picture? And I'm perfectly happy with that bulk picture being crazy and wild and perhaps not even having a path integral description, but I then want to know how that description breaks down and what it looks like either way. But yeah, I agree with everything that you said. Okay. So now the question I have is, how could gravity maybe effectively resolve this factorization puzzle? And the picture that I think we have here is that wormholes, they should be thought of as representing sort of diagonal terms in the product of partition functions, in the sense that I talked about earlier. We have this sum over EA and EB. And then, I mean, literally the terms where EA equals EB should be thought of as corresponding to wormholes or something. But then we should also, and those, of course, won't have erratic oscillations and stuff like that. But then we should also include other geometries or other things to describe the off-diagonal terms. And yeah, even in, that's, I think, quite clearly a step in the right direction in this sense. So to describe these off-diagonal terms, we imagine that in gravity, we can have these, let's say, background boundaries on which spacetimes can end. And as I told in the introduction already, these are very analogous to branes in string theory. So background branes, and we consider theory on those branes. The difference is that we will consider, of course, spacetimes ending on these spacetime branes and not world sheets ending on d-branes. Also for technical reasons, we found that in these dilaton gravity theories, the number of spacetimes that end on these branes is actually restricted to 1. So whereas in a brane and string theory, we can of course have any number of boundaries ending on the branes. Okay, let's imagine now that there are such branes, and we compute a theory on these branes. Let's say you give me the Hamiltonian of a boundary system, and I extract from that the eigenvalues, and okay, then I construct a theory of gravity where I put a brane everywhere where there's an eigenvalue. And I ask what this gravity theory looks like, and my claim is that this gravity theory is identical to the boundary system with fixed Hamiltonian.
Can you elucidate a little bit on what the physical interpretation of that would be? I mean, if I make a black hole, are these branes already there to start with? And do they play a role? Like, if I just make a black hole in the lab, what do the branes correspond to?
First of all, totally lack a Lorentzian intuition for this, so that's already a problem. I guess it's just, yeah, maybe it's something that like looks very close to a black hole, but then there's some other, yeah, it's not precisely the same, or I don't know. I don't know how to think about these things carefully. Yeah.
But in your picture,
It's like a question. What is if you, the black hole is like a saddle of the pattern or something. What is the, yeah, what is the whole pattern? So what are the instanton corrections, and what are the other Euclidean geometries that contribute and stuff like that? I don't know. Yeah.
Mhm.
I guess there should be some structure somewhere or something, but yeah, I don't know how to turn these things into Lorentzian statements.
But some of the pictures that if you don't have these branes, you get an ensemble, and if you specify them, you get a specific theory.
Yeah. Or like the ensemble, and it's literally an ensemble over these brane configurations.
Mm-hmm.
And every brane configuration corresponds to like a slightly different theory of gravity or something. Then when we average over it, it looks like the quote unquote naive theory again. So some sense the ensemble averaging washes away the branes or something.
Mm-hmm.
Yeah. I know that's what happens technically, but I don't know intuitively why.
Can I ask how crucial it is in this is 2-dimension?
Yeah. Oh, you ask how crucial it is that it is 2 dimensions?
Of course, you probably don't know the complete answer, but you're kind of feeling that you already studied and so on, whether there is anything very special you're using coming from the fact that it's 2-dimension.
Well, the calculations are very specific to 2 dimensions, but yeah, I think at least in 3-dimensional gravity, I imagine something very particular happening, but that's of course sort of cheating because we all know that 2D and 3D are similar, and that, yeah, I guess the real question starts from 4 dimensions and stuff like that. Yeah. Yeah, I don't really know, but my feeling is that, like, say you take some 4-dimensional theory, then okay, the bulk is some super complicated string theory or whatever the non-perturbative completion thereof is. But then I imagine that if you zoom to like super low energies, and that everything except for gravity is sort of irrelevant. And then somehow you should still get an answer in pure gravity, I feel, and then the answer should be maybe something like this. So I can't say anything specific, but I think that I feel that there needs to be a sort of solution almost within gravity, and then the next step is to identify how this stuff maybe emerges from a full-on string description or something, but describing like non-perturbative effects in genus and doubly non-perturbative effects in genus and string theory, I don't know where to start. So
great, thanks.
Okay, so imagine again that we have these branes sitting at the positions of eigenvalues of a system. And so our theory of gravity becomes a bit more interesting maybe, or complicated, whatever you prefer. Because now we have these branes to which our probe boundaries can connect. So if you compute a partition function, you get basically a sum over energy eigenvalues, and then geometries where the probe partition function connects to this brane that's just sitting there. And so similarly, when we compute a spectral form factor, then we have 2 of these probe boundaries, and then those can connect to any combination of the branes. Though, like I told you, we'll be finding in these lower dimensional models that the branes are sort of special in that only one boundary can end on them. And so what we can't have, for example, is an analyst starting at one probe boundary and at the other, and them connecting to the same brane. That's not a possibility. So in this simplified sum where I don't count any higher genus configurations with more than 2 holes, I only get off-diagonal terms in this sum over energy eigenvalues. And then, of course, there's still the wormhole connecting the two probe boundaries and geometries like that. So I think you see why this is sort of on the right track if we, at least if we would say that the wormhole itself is equivalent to the diagonal terms. That's of course not obvious, but it would have to be true. Suppose you have gravity plus these branes, then it would have to be the case that somehow we can replace the wormhole equivalently by these diagonal terms. Now, all this, I guess, this intuition of why branes can help us with this factorization puzzle then can therefore also help us encode microstructure. We made this explicit for a two-dimensional JT gravity in a paper, I guess, more than a year ago now, where we dubbed these branes eigenbranes, as I told you for obvious reasons, because they represent eigenvalues. Okay, and those will encode the spectrum of a dual system. And I now want to detail that construction a little bit. Okay, so earlier we established the equivalence of gravitational observables, like the spectral form factor, to observables in random matrix theory. Of course, that's again specific to this two-dimensional setup. In general, it won't be precisely random matrix theory, but we still have random matrix universality, so it would still look sort of similar. And so very specifically here, I want to ask, in this random matrix theory, what do I need to do to make this observable factorized? Now, from the random matrix side of things, that's quite trivial. We can fix all the eigenvalues in the ensemble by inserting additional operators, where each operator is like a Dirac delta that fixes one of the energy eigenvalues. And then that will sort of collapse the ensemble and reproduce correlators in one draw of it. So let me detail that a bit more. So here's a very stupid trick you can do, which still sort of, which I guess is what happens here. Suppose you give me the Hamiltonian of some dual system with a certain set of eigenvalues, and it's like one quantum system. Then I can very stupidly represent that system as a random matrix theory by, instead of considering an ensemble with an ordinary probability density, I consider probability density that's multiplied by a Dirac delta. So yeah, still a random matrix theory, but also one quantum system. Now, as I told you, I can also view this different measure as an operator insertion in the original ensemble with measure P of H. And so if I want to know what the gravity dual is to one single system, I just need to complete this dictionary or these question marks. I just want to know which gravitational operator corresponds to inserting deltas in the matrix ensemble. And then if I insert enough of these operators, I insert a delta, and then on the left-hand side, my ensemble collapses, and I get my single system. And so yeah, these question marks, this dictionary I want to complete, we'll be identifying with these eigenbranes. So yeah, I think it's quite simple to see what you need to do from the random matrix side of things. Consider the partition function, like a z of beta. On the binary side of things, this is just trace e to the minus beta h. So if I inverse Laplace transform that, integral dE e to the beta e, and integral over imaginary beta, then I get a sum of deltas. And indeed, the spectrum of a discrete theory is a sum of deltas. So we find that introducing this is really quite obvious. Introducing a fixed length, a fixed energy boundary instead of a, let's say, thermal boundary in the gravitational path integral, it corresponds in the random matrix side of things with introducing a delta. So what happens if I introduce a bunch of these fixed energy boundaries? I'll be introducing more and more deltas in the random matrix theory, and ultimately the random matrix theory is gone, and it's just one system. And so, yeah, I've identified an operator that does precisely what I want. I'll just introduce a whole lot of these fixed energy boundaries. So that's the picture that we have. You compute, if you want to compute observables in one quantum system, that's equivalent to computing observables in the random matrix theory with a delta on the matrix inserted. On the gravity side of things, that means you're computing observables in a background that includes a whole lot of these eigenbranes, one for each energy eigenvalue of your system. And so the gravitational dual to one draw of the ensemble is JT gravity on eigenbranes. Okay. So again, from the random matrix side of things, this factorization becomes super trivial because I'm just inserting a delta. But from the, let's say, the almost gravitational path integral, it's much less trivial. And I think it's worth developing some feeling for how the gravitational calculations go, because ultimately, at least I want to understand things in terms of pictures of geometries and stuff like that. So yeah, as an example of where I think you can see how things will happen, I want you to consider the gravitational correlator of two fixed energy boundaries. So we sum over geometries like this, and we can compute this quite exactly, genus per genus in JT gravity, by computing the contributions at fixed genus to the spectral form factor and reverse Laplace transforming that. So what you get is like a very, very complicated sum over infinite genus that's asymptotic, but then you can deal with that sum via resurgence and find non-perturbative corrections. It's a whole thing. In the end, though, you find a very simple result that matches precisely with the dual calculation in the random matrix theory. Namely, there is like what appears as a delta, a Dirac delta on the energy eigenvalues, and then some smooth function. And the smooth function is, like I explained earlier, in the two-level spectral density, will be sort of like the spectrum, except when the two energies are close together, there will be a gap in it, which in random matrix theory comes from level repulsion. And this gap you can sort of see happening already at genus 0, because the annulus, it gives something like 1 over E1 minus E2 squared, and so something that sort of wants to decay away when energies become close together. Okay, so
just a question: is that the same thing as this? The two A and B brane cannot be the same. I didn't understand. Like when you were saying like A and B, it has to be different, right? So like two branes.
That's not the same, but I understand where you're coming from. The
Yeah.
reason why I say they can be the same is because literally each row, I'm inserting a bunch of rows here, right? And each row is literally one boundary. And that's why there's only one, like we have literally precisely L of these circular boundaries. Instead of, if rho was a brane, then it would be that each row would be an exponential of boundaries. And I know that it's one boundary because also Z is one boundary. Like, the reason I'm still calling it branes though, but this may be distracting, is that non-perturbatively and surprisingly, one of these boundaries is equivalent to a pair of D branes. So exponential number of boundaries. And in that sense, it's still a brane.
Yeah, but I was asking, can you going back and back and really sorry, but I want to understand this. And going back and like wormhole is a diagonal element type slide.
Another one?
Yeah. Oh, yeah. And then go back one more, I guess. Yeah. So this A and B, you said A and B has to be different. Can you just elaborate? You probably said that, but I just.
Yeah, that's because of these. So I will have, say, a boundary for each, and one boundary for each energy eigenvalue. So I have L of these boundaries, rho of E1, rho of E2, rho of E3. So these are L, let's say, dots where your geometries can connect to. So what I can't have is, if I have two probe boundaries, they cannot both connect via an annulus to the same dot. Because the geometry that does it is actually trivial sphere. It's not two annuli. And so if I only restrict to annuli configurations, yeah.
Okay, thanks. Yeah.
Because that's why there are all these dots here, and there will also be dots on this lower part. There will be more complicated geometries, but the picture is clearest when I restrict to annuli. Also, for the higher geometries, there are also exclusion principles like this. But yeah, I think this is the most intuitive picture. Okay, so after increasingly more complicated calculations, you ultimately find that, in fact, you only have the deltas and all the smooth crap goes to 0. Yeah. Anyway. So now I think final thing I want to say about this is I want to sort of visualize a picture I went back to earlier and just say that it's precisely true in JT gravity. I guess I already said it in the past few minutes. When I compute the spectral form factor, we have these L dots, these eigenbranes where you can connect to, but they can never connect to the same one. But still, we have the wormhole, and so this still needs to be true. But we can in fact check that it is true. The calculations are quite messy, so you need to sum a whole lot of terms on left and right hand side, but then you can just do this numerically with increasing precision, and you just see those sums becoming equal. And again, we know that's going to happen because from the random matrix side of things, they're precisely equal. It's just, I think, rewarding to see it happening from the gravity point of view. So this thing is true in JT gravity. Unfortunately, it is complicated, and I think that's sort of annoying. I feel that there still needs to be a much easier way to see all this happening, but I haven't figured that out yet. I mean, these eigenbranes are a way of making the discreteness manifest, but it should be. I feel like discreteness should be more obvious from the block point of view than I've realized it until this point. But yeah. Anyway, that's all. Actually, I have some conclusions. So what have we seen today? Well, first of all, we can reproduce the averages of late-time boundary correlators in chaotic systems in bulk gravity by including wormholes and summing over particle propagators also on those wormhole geometries. Furthermore, we've seen that there are cases, though it didn't a priori perhaps needed to be the case, but I wanted it to be the case, where pure geometry can be smart enough to capture the microstructure of a quantum chaotic system. Though, of course, it becomes sort of iffy what you call geometry here. And yeah, in this case, the eigenvalues and eigenvectors of the quantum system, they get encoded as boundary conditions of background branes in the gravity theory. Okay, and one question is I have, which you all also have, is how this generalizes to higher dimensions. I don't really feel like the answer here needs to be something complicated in string theory. I think the ramp and the plateau are so universal that they need to have a sort of simple answer. And I think simple in this case should mean geometrical, because yeah, it really can't depend too much on the theory. Then one last thing I wanted to say that I think I would, maybe like to look into, so Outlook or something. So as I told you, we should view these. We can view gravity on a bunch of branes as really just another theory of gravity, literally with a different Lagrangian or action, whatever. That's sort of open-closed string duality at work. And I think that's made very manifest by some recent work that people have been doing, where, for example, something you can do is consider dilaton gravity series that are not JT gravity, but with a literally different action, but then they're equivalent to considering JT gravity on a bunch of branes. And you see very clearly on the matrix side of things and also on the bulk side of things that it's just gravity on branes. So the question I have is, now say I don't take those, let's say, defect branes or whatever they are. I just replace them with the eigenbranes I discussed here. Then, by the general idea of open-closed duality, that should still define for me just a theory of gravity that has literally a different action. And I would like to know what that action is. I think the dilaton potential should somehow have encoded in it all the eigenvalues, maybe as Fourier components or something, I don't know. But notably, that theory, I mean, if that works out, that theory should factorize by itself. And I don't know how that would happen. So maybe the wormholes become 0 or something. But yeah, I mean, that's something I think to look at. Thank you.
So let's
Sorry for this
Andreas.
chaotic ending.
So now if we have some questions. Andreas, I think you sort of responded that before, but if you still can have a little to say about whether there's some interesting things to be thought about in Lorentzian interpretation of these results, or it's kind of like, it seems a lot of it is like a very nice rewriting of the partition functions and things like that. But I was just wondering if there's, even from a technical perspective, if you think there's like an interesting route for that.
I mean, there should be, right? But the zeroth order question could be something like, say I have a theory of gravity and I just add one brane to it. How does that look? What does that look like? I mean, not necessarily one of these eigenbranes, just the standard brane that we know from 2D string theory. And what does that, if I interpret that in a Lorentzian way, what does that look like? I don't know what the answer is, but that would be the first step, I think. Okay, yeah.
Am I understanding correctly that, say, if you think about some like a matrix integral in the boundary side, and you can have continuously different eigenvalues. So do you have continuously infinitely many these branes, types of branes?
Yeah, because the branes are labeled by the boundary conditions we can have in these theories, and these theories JT, you can think about it a little bit like a Liouville theory or something. And the branes of Liouville theory, we have these FCZT branes, and those have a continuous parameter. And the same continuous parameter there is literally with the one parameterizing energies. So we have precisely the correct amount of data to do this.
Do you think it has leads to the problem if you have a propagating graviton, which coupled to kind of these infinitely many objects in, let's say, loop or something? So that may be one specific to lower dimensional situation.
Yeah, I have no idea what happens when propagating gravitons come into place.
Yeah.
Though
But gravity universally coupled to things, right? And then you have infinite type many data types, usual. Anyway, of course, nobody knows, but yeah.
There are so many questions about the higher dimensions.
That's right. That's right.
I think this this is what I would ultimately want to know. But the first question is probably, the wormhole part of the thing, right? I mean, people are worried about these then stringy D-brane instabilities in wormhole geometries, and that needs probably sorting out first. Like find the ramp in higher dimensions, and then start thinking about plateau and then about oscillations or something. Yeah, I think a million things could probably go wrong, but we have a lot of problems to solve before getting there.
So any more questions?
I had a question. So you focused here mainly on the spectral form factor, but let's say you try to do the page curve computation. For example, in like the eternal black hole coupled to a bath kind of setup. In principle, if you could include the eigenbranes, would you be able to find noise in the page curve that you wouldn't find if you just did the usual Euclidean path integral computation?
I was told that the page curve is self-averaging, so there shouldn't be noise there. So somehow all these off-diagonal contributions should cancel out. I mean, it will happen in the same way that it does in the boundary calculation. I mean, the reason, I don't know why there's precisely why there's no noise on this page curve thing, why it's self-averaging, but it means that these phases sort of cancel. And then if the bill calculation will just reproduce the boundary calculation, so then the phases, I guess, will cancel too. And only the diagonal pieces will be, the wormholes will be important or something. So I guess if you compute,
You could still, it would still be interesting, I think, to try to study Lorentzian dynamics, black hole formation and evaporation just in 1+1 dimensions. I mean, there's no reason why we couldn't try to do that, right? It would be interesting because it would be nice to see what the effect is of putting these branes there.
Yeah. I mean, I don't really know what calculation to do or something. Maybe you guys know.
No, I don't either, but I think it would be very, well, maybe it's not a well-defined question, but if it's not why, I mean, it seems like this choice of branes defines a theory in some sense.
Yeah.
And if that makes any sense at all, then it should be possible to do something like that in a Lorentzian context. And then you could look at what effect that might have on the bulk description of the horizon, for example.
Yeah. No, that's a good, good question. Yeah, there are some things to do, I guess. Yeah, I don't have anything more to say about it. As you probably figured out by now.
Well, it seems really interesting. I mean, so you can't do everything in one step, but this seems like a really interesting direction to pursue.
Thanks. Yeah, I think personally, I think the way to work with these things in the gravity context is maybe to start with like a few of them or something. Because if you have like all of them fixed and the theory becomes sort of wild and it becomes like literally just a discrete sum, and that's sort of maybe too boring or something. Though it's ultimately what you want, but I mean, the nice thing is, I think if you fix like a few eigenvalues or something, then if you compute like the spectral form factor, you get like a few wiggles. It's just not that erratic, but you already get a little bit of stuff. And I guess it would be nice to see also maybe in this page curve thing or something, what would be the effect of fixing one eigenvalue or something, or two eigenvalues, if that makes sense. Like, don't go to the super extreme That's no, okay.
Yeah, I guess
The
one problem is
Lorentzian thing I need to
that you
think
have to
about.
decide ahead of time how big your black hole is. So some sort of naive picture where you just make the black hole and let it evaporate probably doesn't work, but maybe something like what Venn had in mind.
Yeah.
Um,
Yeah, something eternal, whatever. Yeah.
Yeah.
Sorry, you go.
No, please, Van. I was gonna ask if somebody wants to
Okay.
ask. So
yeah, I had a bit of a naive question. So in this last slide, when you talk about different dilaton gravity theories,
Yeah.
Do you have in mind like deformations of dilaton of theories where you add brane contributions to the action?
Yeah. So the things I have in mind specifically are two things. One is these, you know, that Maxfield-Moralv and then Witten. No, it's not Maxfield-Moralv. Sorry, it's Maxfield-Turiachi and Witten. Sorry, that's a habit. They had like this theories of dilaton gravity with a different potential that's not just phi, but you can have like e to the minus alpha phi things, sum over alpha, whatever. Right. And those correspond to inserting a brane of defects in JT gravity. And the word brane here basically comes because it's just exponential. And so, and a defect is like a boundary condition. It's a small boundary, not a large boundary, but it's quite the same from the mathematical point of view.
Okay, yeah, that was basically what my question was, because so yeah, the way I understood those was you're inserting conical defects into your manifold, whereas here seems like you're modifying the boundary conditions by, you know, allowing your geometry to end on fixed energy branes. Are these?
They're not the same boundary conditions, but still, I mean, a geodesic boundary is just an analytic continuation of a defect boundary, and then geodesic boundaries are complete and whatever. So I feel like I haven't looked at it carefully. I was actually going to very soon, but I feel like these defects and these, yeah, I feel like an analytic continuation of that stuff to geodesic boundaries, I don't think it's unimaginable. And then once you're at geodesic boundaries, then you have whatever you want, because any type of boundary condition you can decompose into geodesic boundaries. Like the trumpet would be the overlap, basically the transformation rule between the two. So, I mean, I can imagine, it's not precisely the same, but still I can imagine something like that working.
I see. Okay.
Oh, and the other class of theories I had in mind were the minimal strings, which are like dilaton gravities with a singe potential. Those are also random matrix theories. And there is very well known that you can get any minimal string theory from what is called the Airy model by inserting a shitload of branes. So in that sense.
I see.
And JT gravity is one of those minimal models, and you can go from any of those minimal models to another by again inserting branes. So yeah, in that sense, it's again a deformation of JT gravity.
Okay, thanks. Yeah. I had one more vague question, which is, so I don't know if you know of this, I think from last year or something by Lorenz Eberhardt.
Yeah.
Yeah. Okay, so in 3D, he has a similar kind of pictures, except there the like, you know, the wormhole is supposed to be coming from excitations of tensionless strings as opposed to adding space-time branes. Do you have like some understanding of how these might be connected if you were to think about this story in 3D? Or because it's like it's a very similar story. It's just the degrees of freedom that are giving rise to the like wormhole, or in one case stringy, and in this case they're coming from the gravity path integral. I'm just curious if you've thought about the connection between these.
Yeah, I've had trouble thinking about this stuff because I don't see the gravity clear enough. So I don't have anything super intelligent to say, I'm afraid. But yeah, maybe if I see the stuff which he and his collaborators did, which is like super interesting. The question I have with that is, can I take that and sort of zoom in on a region where this becomes like only gravity or something, and then what happens? Because like it's super cool that in the string theory there is a factorization puzzle, presumably, but then again, maybe I would have expected that to happen in string theory. And then maybe the thing I want to see is how does that, can we understand why that happens or something? Is that, yeah. Can I get a scaling region out of that or something that I can draw effectively what's happening or something? I guess I would like to draw pictures.
Yeah, I guess what I was wondering is, I think you might have mentioned it earlier in your talk. If you actually want to do a gravity computation with these branes, it's pretty much impossible, right? Because the number of branes is so large that you lose the semi-classical picture.
Yeah.
So is it possible that ultimately the only way that there is no gravity computation? You just have to use string theory, or?
Yeah, but what? Yeah, that's possible. Yes, but I think what's nice here, for me at least, is that you can sort of you don't need to go all in from the start. Like I said, you can consider 1, 2, 3 of these eigenbranes, and you already see stuff happening, like there get more wiggles on the spectral form factor, and the theory edges towards factorization. Like if you fix a few of these eigenvalues, then and you plot like the spectrum as computed in the theory, you see it's like the normal spectrum, except that here there's like a whole region where it gets like depleted and with some energy spikes in it. So you can sort of see it happening, and you don't need to go to this limit where you lose all control, where all the energies are fixed. But yeah, I mean, yeah, that's the valid point. I mean, there's no real gravity description, I guess, of the extreme scenario. Then I'm just making pictures based on the place where gravity still makes sense.
Mm-hmm. Yeah, thanks. Yeah, that helps clarify it.
Yeah, so if nobody else has questions, let's thank Andreas again.